My name is Derek Carter, and in this video, we're going to continue looking at the APIs that we're going to be using in this course. So previously, we dug down a little bit into the details of the TensorFlow API, which will be useful for us. But this time, in this video, we're going to look at the high-level Keras API. So, not everything, but get into a little bit more of the details of how it works, what's in it, things like that. Okay, so we'll start by talking about layers, right? So the fundamental data structure of a neural network is a layer. So there are different kinds of layers. That'll be one of the big things that we'll see in this course. But some layers don't have any parameters. They're stateless, but most layers do. And a typical layer acts like a single set of weights and biases, just like we did in the previous example where we were doing the linear classification model. So, that's kind of the prototypical idea of what a layer is doing. It has a set of weights and biases, and it's performing an affine transformation every time you give it some inputs. It does that. Its tensor transformations on the inputs, resulting in a new tensor that's sent as an output that can be chained to the next layer in your network. So, a layer takes an input as one or more tensors. We'll see some examples where you have more than one coming in. And output one or more tensors. So I already mentioned some layers are stateless, but most frequently they have, like this one, have a state that gets modified as part of the learning process using gradient descent optimization. So a lot of this class we will be learning about the different types of layers that you can use with Keras, so convolutional layers and recurrent layers and some other things. But yeah, you can think of these as sort of Lego bricks. So the reason why the Keras API is high level is it's got the bricks and you can put them together relatively quickly to make sophisticated deep learning networks. So Keras has an object-oriented design. So it might be a good idea to review a little bit about doing object-oriented designs in Python. I should have some materials for doing that in my class if you need to. So it has a layer abstract base class. So all layers in Keras are actually child classes or subclasses of the layer abstract base class. So in this example, we're just building a dense layer. There's already a dense layer in Keras, but we're going to recreate some of the basics of it if you walk through this example here. So you can look at, so we're inheriting from the Keras layer that's in the layers sub module of Keras. So that means that we're a child of the base layer class. And we only define three methods here. The init, so notice, so the layer base class will define a bunch of member methods. We can override those. We could override them, but chain so that we could do some of our own work, but have the base class do some other work for us. So for a basic dense layer, we're going to have a set of units. We have to keep track of what our activation function is. Although you can have layers without an activation function, they just take whatever the outputs are after the affine transformation, and that's sent on instead of going through a nonlinear activation. The build method, if I remember right, that is what happens when you compile a network or something around in that part. So that is where we this gets invoked in order to create the weights and biases for a layer. So we could have actually just directly used TensorFlow variables if we wanted to. But here we're showing there are convenience methods. Again, this is coming from the base class, layer class. So I believe if we went and looked at the code for this, it's basically creating a TensorFlow variable of the shape you ask. And so if you ask for an initializer of random normal, it would give you probably some small random initial values for your weights of whatever shape you ask for, or you could ask for weights all starting at 0. And the call method, that is actually what happens during the forward pass. So you can see that we're expecting that W and B are TensorFlow tensors. So, and we're doing the basic thing that we've seen so far, a matrix multiplication of the inputs times the weights, and then we do a tensor addition operation, and that's our result. And if activation function is supplied for our dense layer, we pass the outputs through the activation layer before we return that. And that return value would be what would get sent to the next layer after us if we're building a network using our layer here called simple dense. Okay, so let's run that cell. So we define our simple dense class, which inherits from the layer-based class. So once instantiated, a layer can be used just like a function. Or the way I would say that is, here in Python, we're instantiating an instance of our simple dense class by calling it like this. So we specify an RELU activation function, and we say that we're going to use 32 hidden units in our simple dense layer. We can invoke here's where we're using it like a function. So if you use it like a function and you pass in an input tensor, the call method is ultimately getting called by this invocation here. So the result will be an output tensor. In this case, we should have a tensor of it will depend on the shape that we set. So since we have 32 hidden units, the 784 features that come in get transformed into 32 features on the output. So we're going to end up with, we have two samples, and you can think of this as having 784 features that come in as input, and doing our affine transformation. We still have the two samples, but they've been summarized as 32 features on output. So a little bit more about those build and call methods. I was a little bit wrong about what I was saying there. If you look at the example we just did, you'll see that we actually used our myDense instance of our simple dense layer without ever invoking build or call. So again, if you know a little bit about Python, the way object-oriented functions work, the call method is what gets called when you do something like we did right here. When you take something that's actually an object, but you invoke it as if it's a function. Ultimately, the call method will get called. We also never specified like the input shape. So the call method, going back to here, the build method needs, for example, the inputs so it can build these shapes for the weights and the biases that it has. So one thing to understand about Keras is you can only clip together layers that are compatible. So that ultimately means that you have to worry about the shapes. So it's usually not the samples dimension. So the first dimension, I can pass in for this layer to transform me, something with 2 samples or something with 10 samples, or however many samples. But once it's been built, it's going to always have 784. It's going to always expect 784 features coming in of however many samples that we give it. Okay. So in this case, since I redid this cell where we passed in 10 samples, now we get 10 samples in the output that were squeezed into the 32 output dimension features for our transformation that we just did. So you have to keep that in mind. So you can only clip together layers that are compatible, which mainly at this point you can think of that as it expects the input to be of a certain shape, and it's going to return output tensors of another certain shape. Again, it's the first dimension is usually variable. That's our samples dimension, but otherwise, this is going to be expecting that it's going to be outputting, in this example, things with 32 features, 32 dimensions on its output for however many samples we're given as input. So yeah, so it can only be connected to a downstream layer that's going to expect a 32-dimensional vector as input for it. But Keras tries to infer the sizes and compatibility for you, so it reduces as much as possible what you have to specify. So for instance, if you create two layers in a sequential model in sequence, the first layer didn't receive any information about the shape of their inputs, right? Or in the second one also. So these are automatically going to be inferring their shape of the input, the number of dimensions in the input from the first inputs that they see. So really, if you look closely, I mean, that's what happens here. So however build gets invoked, the input dimension is just inferred. So build should only get invoked once, and it gets invoked like just in time. So only the first time it's needed is when this build will get called to create the weights and initialize. So yeah, to summarize that, the build layer is called automatically the first time the layer is called. Likewise, that underscore call underscore method that gets invoked automatically when you invoke a method instance as a function, that gets called for methods that are derived from the base class each time that calls the call method to actually perform the forward pass. So a deep learning model is a graph of layers, and there's a correspondence between the graph of the network, the deep learning network graph, and the computation graph that we talked about before. So you can create a model graph using the model class. So we've only seen examples of a sequential graph. So where the inputs go through layers in sequence to the outputs. That's the simplest kind of graph you have. And there's no cycle, so it's acyclic. But as you'll see in this class, you can have much more complex graphs. So you can have branches, so things branching out in your graph. It allows you to process more than a single input layer. So branches going out or branches coming in. You can have cycles. So some of the layers we'll look at use cycles, so they're not acyclic anymore. They have a cycle in them. So we'll talk more about this, but that topology kind of defines a hypothesis space. So that's what's possible for the model to be able to represent and do and transform the data that it's given to learn. So you'll use the data and make assumptions about it. Now define what can be learned, but that hypothesis space is extremely important for this concept. It encodes the assumptions being made about the problem, and so if you don't understand your problem well enough, you might be making assumptions that aren't warranted by the problem that you actually need to solve, and you won't get very good results. So that's kind of the art of designing deep neural networks, and that does take some experience. So you have to do, as you do more and more of these kinds of designs of architectures, you get a better feel for what kind of a model of your network you need to do in order to do well on certain kinds of problems. But yeah, if you use this textbook and read it, there is some summary of some best practices, at least of the state of the art in 2022 when this textbook was published. So once you've created a model architecture, and as we saw in our first example of using Keras before you maybe understood too much of what was going on, you have to invoke the compile step, if you remember. That's where you specify the things that you need in order to control the training of the model using gradient descent. Right? So you need the loss function and the optimizer in order to monitor then whether your training is working or not, you usually also have to specify metrics for you, right? So these are different than the loss function. So the loss function gives a signal for how to modify the weights, but that may or may not end up giving the ultimate success for what you want to do. For example, getting the highest accuracy that you can on classifying the M and IST digits, like we did in our first example with the Keras API. So, so the basic workflow, you define your model by creating layers and putting them together into some type of a model that has a particular graph. Then you call the compile method to set your loss optimization and evaluation metrics. Once you have those parts, then you are ready to call the fit. So that's what controls the gradient descent. So by default, it's going to be using the stochastic gradient descent version in order to fit the models to the parameters. Make certain I don't think I did all these cells here. So here we in this example, we're creating just again a model, a sequential model, simple graph with two layers, just two dense layers. Or in this example, again, we create just another model, sequential model, just has a single layer in order to just demonstrate calling the compile on it, right? So it might be the same things that we used before. So we're using the RMS prop optimizer with a simple mean square error, and we want to have overall accuracy as kind of the metric that we monitor during our fitting training. In this class, you should become familiar with the different kinds of loss functions. So that's kind of an important decision to make. So there's certain kinds of loss functions that you need for classification problems and certain kinds that you need for regression problems. So you do need to make some consideration. It's extremely important to pick the right one. So as you do this class, you'll pick up a few of those, at least the first ones that you use basically for whether you have classification or regression, and then maybe a few refinements on those for, if you're doing image classification or you're doing text classification or something. So as we saw already, after you do compile, you're going to do the fit. The fit method implements the stochastic gradient descent training loop. So for fit, as you might expect, you have to pass in the data and then the targets for that data. So those are the kind of the only required things. Then you can specify other things, so like epochs, the number of epochs to train, the batch size. There's ways to specify, for example, that I want to do. You can just set the batch size to 1 if you want to do single batch training, or there's ways to specify to do like a full batch, so on. So here, this is kind of just a random model, but we're showing it running 5 epochs on our inputs and targets here. I forgot to mention that we are using the same inputs and targets that we used in the previous TensorFlow example, so we've got those loaded in here now. To try it again, but with the Keras API. So the fit method returns this history object, which is kind of really just a dictionary. So yeah, here we can take a look at it. So it's really a dictionary. So we use that a lot after we do training in order to evaluate the performance. So I think, yeah, that you normally only get like the accuracy and the loss. So here we're seeing basically what we had here that's output by default. You can suppress this output if you need to, but the output that's shown when you do the fit. So for each epoch, we were getting the loss, and we were getting the metric we asked for, so the overall accuracy that we were getting on the data. So again, this is the same history. We could use that for plotting or doing some other sort of evaluation. So the goal of machine learning is to obtain models that do well in general. So just because it's performing perfectly on the data it's trained with doesn't necessarily mean it's a good model. So this is really what we'll talk more about this in this class, but this is really what the test train split is about. when you train it with a portion of training data, and while you're training, if you reserve a portion that you don't train with, but you evaluate how it's doing on your loss and your other metrics you're interested in for each epoch of the training, that's usually called a validation data set. So same idea as testing data and training data, but the difference is usually people mean validation data is data that we're going to be used during the epochs of a fit to monitor the generalization, how generalization is evolving while the model is being trained. So here, I mean, most of this code here is just in order to split the original inputs into a training and validation set. All right, so the original inputs were not shuffled up, so we need to be careful that we don't end up with only one class in the data that we want to validate with, which is why we shuffle up here. But basically what's happening is we're taking 30% of the data, holding that back for validation, and leaving the others for inputs. But otherwise, we just do the same thing we did before. Have our model, compile it, and run it, fit it on 5 epochs here. But now we pass in the validation data so that we'll get a report of what's happening on each epoch on data that was never trained with. Right? So so even though we're getting 96% accuracy, or actually I was a little bit surprised by that. I have to go back and look at that if that's usual or not. So it'd be more usual to getting to have overfitting. So this is one way you can check for overfitting if you're getting like really good results on the accuracy, but when you go and look at the accuracy on your validation, it's not doing very well at all. But anyway, I mean, by getting validation data, we're reporting both the loss and accuracy on the data it was trained with and this validation data that the model actually never saw during the training. And then finally, once you have a model that's been fit, you can evaluate it on here on the validation data again, or we might have yet another data set to give a final testing performance, the test data set. So here we can see that we're getting 99% accuracy on the validation data for our model that was trained. And for a training layer, if you want to do inference, so once you're satisfied with your model, you might want to put it into production. So here, given a model, so there's mechanisms in Keras you can use to like save a model and then just reload it, and then you might put that into your front end in order to do predictions, to do inference for customer preferences or things like that. So here we're using the predict method to predict on against some inputs, but it could have been a totally different set of inputs here that we do inference or prediction. Okay, so that's it for this video. Hope that was useful for you. So just to summarize a few things that we went over on here. So we looked at just a little bit of some of the details of Keras. A lot of the stuff, we are going to be filling in a lot of the details on here. But you should now be kind of aware that some of the basics, so the idea that Keras is a graph, any neural network is really a graph of a sequence of layers. It doesn't necessarily have to be a sequential sequence of layers. So part of this class we will see some more complex network graphs. But then Keras, has mechanisms then for compiling that into our model so that we can figure out what our loss function we're going to use and the optimizer that we'll use and what metrics we'll use for the actual evaluation of how well the model is doing. And then the things that we saw here in the end is that the fit method is the one that actually runs the gradient descent using the optimizer to train the weights, reduce the loss, hopefully improve the performance of your model on the data set. So that's it for this video. I hope you found it useful, and I hope to see you all guys in the next video.